class, we learned how to solve optimization questions. And we learned that there were 4 different types. We had our type 1 with like our revenue cost profit. Our type 2 involved like fencing problems. Our type 3 was those like weird change questions that we did. And then our type 4 was just everything else. So we've already done 2 type 1 questions. So today we're going to continue on with this worksheet, and we're going to go back through and do each of the other types of questions just one more time to make sure that you guys are comfortable with optimization. So I want you guys to read question 5. There is a line missing from question 5, so let me add it real quick. Okay, let me know in the chat when you are done reading question 5. Maybe. I haven't seen an eggplant in a really long time. Okay, I think that's most of you. So what type of question do you guys think this is? So remember, type 1 were the questions that involved profit, revenue, and cost, and the formulas for them. Type 2 were our fencing problems. Type 3 were our problems where we had one thing changed as another thing changed, and type 4 was everything else. So what type of question do you think this question 5 is? Tell me in the chat. It's actually not that bad, I don't think. No. So what do you guys think? Is it type 1, type 2, type 3, type 4? Just kind of remind you guys. Type 1, using the formulas. Type 2, the fencing question. Type 3, our orchard questions. One thing changes and another thing also changes. And type 4 was everything else. All right, that's a few of you. Good job, guys. So this is a type 2 question. And remember, type 2 questions are the type that I usually think are the most challenging because they really involve doing step 2 for optimization. So our first step here is to figure out what we're trying to optimize. What is the function I want to optimize here? What function am I trying to optimize? You got it, Alex. Here it says maximize. I want to maximize what? Total area. So the area of the whole thing. So we also have said that with type 2 questions, I'm just going to go back over here and kind of remind us that trying to optimize some type of space or given some type of space, like area or volume, step 2 is necessary. And we also said that it's often useful to draw a picture when we're dealing with type 2 questions. So we're going to draw a picture of this thing. We have a rectangle. This is question, which number was it? This is question 5. So they have this living area. And they want to separate it into 3 spaces using their seaweed. So in other words, we have something like this going on. And now I don't know what size this thing is. So I'm gonna say, let's let that length be X and this length be Y. So we've drawn the thing. If that length is X, then that's also X, and that's also X, and that's also X. So in my first step, we want to write down the function we are trying to optimize. So here we want to maximize area, and we want to maximize specifically total area. So in other words, not just the area of one of their spaces, but the area of the whole thing. So what is the area of the whole thing? What's the area of a rectangle? Good job, Alex. Good job, Luca. This is just X times Y. So it's the length times the width, or the base times the height, however you want to think about it. My area is X times Y. So this is area in 2 variables. Now our second step says that if your area, or if your function you're trying to optimize is in terms of more than one variable, I want to use the other information from the problem that I haven't used yet to rewrite area in terms of just one variable. So what piece of information from this problem have I not yet used? You got it. I haven't used the 1,000 meters of seaweed. So what they're doing is they're putting seaweed around this whole thing. So here's what I know that I haven't used yet. I know that there are 1,000 meters of seaweed to go to cover all of the lines that we see up there. Okay, so I'm just gonna draw some lines in red. Am I putting seaweed here? In that red line I just drew? Am I putting seaweed here? I'm separating the rooms with the seaweed. So they decided to separate their common living area into 3 equal-sized rectangles using that seaweed. So the seaweed is going there. So is the seaweed going here? Is it also going here? Is it gonna go here?
Yeah.
Is it also gonna go here? Yes. So I know that I need seaweed in all of that pink space that I just drew. So basically on every line that I had there. So I have the length is X. How many X's do I have? How many sides of length X do I have? I've got 1, 2, 3, 4 sides of length X, plus how many length Y sides do I have? 2. So I have 2Y. So this right here, it turns out, is the perimeter. It's also the amount of meters that need to be covered by seaweed. Okay, so what should this equal? I want my seaweed to cover that whole thing. So this is going to be my relationship between X and Y. That's going to allow me to rewrite area in terms of just one variable. Now, we've said that once we have this relationship, we want to solve for one of the variables. Does it matter which variable I solve for? It does not matter. I can solve for X, I can solve for Y, it doesn't matter. However, we've said that typically we solve for Y because then everything will be in terms of X and we're just used to working with X. So I'm going to solve for Y. I'm going to get 2Y is equal to 1000 minus 4X. So Y is equal to 500 minus 2X. Which means that my area function is equal to X times 500 minus 2X. In other words, area is 500X minus 2X squared. Which brings us to step 3, because now that I have my area function in just one variable, all of the steps are the same from here on out. Find the critical values, apply the second derivative test, answer the question. So this is area in one variable. And now everything is the same as all of the other optimization questions that we have done. A prime is going to be 500 minus 4x. So I want to know, where does A prime equal to 0 and where does A prime not exist? So here I'm doing 500 minus 4x is equal to 0. 500 is equal to 4x. X is equal to 125. Where does A prime not exist? Never.
So it's constant.
You got it. So what is it? What exactly? So A double prime is always constant. So here we go. So we're going to have A double prime is equal to -4. Is it a problem that A double prime is constant? No, that's allowed. All that means is that this is concave down everywhere. So in other words, A double prime of 125 is equal to -4, which is less than 0. So this is concave down everywhere. So is X equals 125 a max? So X equals 125 is a max. So then step 5, we want to answer the question. And the question is, what should be the dimensions? So how am I going to solve for Y to get dimensions? What do I need to do to solve for Y to get dimensions here?
You plug in the X into the area formula, then with the area and the X, you could find the Y, and then it gives you all the dimensions.
So I can absolutely do that, but do I also have a value for Y in terms of X right here?
Oh yeah.
So like absolutely I could do what you said, and that's definitely one way to do it. Find the area and then figure out what Y would have to be. But I could also just plug into that. So 4x minus, or Y is equal to 500 minus 2x is the thing that we have. So what we said is, with type 2 questions, we always want to go back to our relationship in step 2 to find the other variable. So here we got that X is equal to 125. So Y is equal to 500 minus 2 times 125, which is going to give me 250. So the dimensions to maximize area are 125 by 250. So, Kiana, in most semesters, there are 2 optimization questions on the final. 2 optimization questions, and they're just picked randomly from the different types of questions, so you never know which one's going to show up. But this semester, with our final being an hour less, it seems likely that there will only be one. And you just have to hope it's the one that you're best at. Okay, are there any questions about this problem? Okay, so I'm going to go back up to the questions and we're going to look at question number 7. I want you guys to read question 7. Tell me in the chat when you're done. There we go. Now we have an eggplant. So when you're done, you can start thinking about which type of question you think this is. Is this a type 1, type 2, type 3, or other type 4? Yeah, good job, Lucas. So you should be either telling me that you're done or telling me what type you think it is, 1, 2, 3, or 4. Yes, good job, Michael. Yes, good job, Maureen. Yes, Alex, good job. I'm gonna give you guys a few more seconds to tell me what kind you think it is. What is Sandy listening to? All right, guys, I want to be hearing what kind of question you think it is. Type 1, type 2, type 3, or type 4. Come on. I've heard from like 4 of you. So remember, type 4 is other. Type 3 is when we have 2 changes happening together. Type 2 is what we just did. Type 1 is the profit, cost, revenue thing. Yes. All right, guys. Okay, good. That's a bunch more of you. So the answer is that yes, this is a type 3 question. Almost all of you got it. So this is type 3. So I'm just going to go back over and read the notes that we wrote yesterday about type 3 questions. Type 2, type 3. Type 3 we called orchard questions. And they were questions where if one thing changes, then another also changes. For example, an increase in people causes a decrease in price. So in this test question, we have steps 1 and 2 are combined, but we also said for type 3 questions, we want to start off by defining a new variable that represents a change. So before I do anything, I'm going to define my new variable. So here we're working on question 7. And I'm just gonna start off by saying X is equal to the number of changes. But then I want to think about that in the context of this question. What are the things changing in this question? So like, what could that X be? What are the things that are changing? Come on, guys. Let's think. Let's get engaged with math. What are the things that are changing here? Also, this is a really boring question. Maybe if I ask you guys what we should sell first. Units. So what should our units be? Let's start there. I've got price and units. Yes, good job, Alex. Good job, Maureen. Those are the things that are changing. The price is being reduced. The units are being increased. Those are my changes. What should my units be? Because this is really boring. What should I sell, guys? Let's use our creative energy. Come on. Something. You guys gave me some good things last time. What are we going to sell today? Pineapples? Okay, we could sell pineapples. Oh no, we're not going to sell. We're British people? Okay, why don't we sell some golden pineapples? I like that. We'll sell some golden pineapples. We're not going to sell people, guys. Like, are you guys the class that wanted to sell children? What are you going to do with you guys? Okay, so pineapples. Okay, and then as you guys said a second ago, also we're not selling cheat sheets. Come on. Also, as we said a second ago, the things that are changing here are prices being reduced, more units are being sold. So this could be our changes, could be the number of price reductions, or the number of times units increase. Yeah, I like that. That's good. So golden pineapples with miniature British people. Wait, but then you're gonna eat the British people. And that's maybe weird. Okay, so now we can move to our very first question, or our very first step of optimization, which is to write down what we are trying, the function we are trying to optimize. What are we trying to optimize here? What's the function we want to optimize? You guys are just not with me today, are you? Yes, thank you, Alex. Thank you for being here today. Maximize. I think it's David's not here. Where is David? That's why I'm not hearing the answers. To maximize revenue. You guys are having to like make up for the fact that David's not here today. You've become the new David. Yes. Okay, so we want to maximize revenue. So that means we're going to write down our revenue function. Revenue in this case is golden pineapples times price per golden pineapple. So we're going to write that down. And in this question, with these, we said that 1 and 2 are done at the same time. So my revenue is equal to number of golden pineapples times the price per pineapple. And what we said is that we want to write each of these in terms of the new X, the new variable that we have. So I'm writing each of these in terms of that X right there. So I want to know, how many golden pineapples do I have? And what is the price? Okay, So what's the base number of pineapples that I have in this question? What's my base number of pineapples? 500. You got it. 500. And when my units increase, how many are they increasing by at a time? Am I increasing slowly by 1 unit at a time, or? So I've got 500 golden pineapples to start. Good job, Sandy. I'm then increasing by 20 units. So what that means down here is that this is going to be 500, my base number of pineapples, plus 20, the number it's changing by, X. What's my base price? What's my base price here? 31. And how much is my price changing by at a time?
$1.
$1, you got it. So then I'm gonna have 31 plus 1x. So this is 31 plus 1x. And so that was from the blue stuff we highlighted, and this was from the purple stuff we highlighted. Good. So this means that my revenue function is equal to 500 plus 20x times 31 plus x. So now we can move on to step 3 because I have revenue in terms of just one variable. And that's what we want. So we want now our step 3, 4, 5, always the same, critical values, second derivative test, answer the question. So since I need to find my first and second derivatives, it definitely makes sense for me to expand here. So I'm gonna get 500 times 31 is 50. And then I'll have plus, am I increasing the price or decreasing the price?
Decreasing by $1, no?
So I'm decreasing my price. So what's wrong with my price per pineapple that I have there?
-1.
It should definitely be -1. Good job, Michael. So that should definitely be a -1 because I am decreasing my price. So be careful about things like that. We're decreasing the price by 1, so we're not increasing it, which means this is actually going to change. So this is 31 minus x, which makes way more sense because now I can actually get this 120x minus 20x squared. Okay, so now I'm going to find r prime, which is 120 minus 40x. And then I want r prime is equal to 0, and r prime does not exist. So at this point, we've done steps 3, 4, and 5 so many times today, yesterday, and last Thursday that hopefully you guys are like starting to remember what they are and how to do them. So 120 minus 40x. I do 120 minus 40x is equal to 0. Which gives me 40x is equal to 120, which gives me x is equal to 3, and then r prime does not exist. That never happens. So then I move on to step 4, which is now to find the second derivative. And you guys might be noticing that a lot of times with these questions, the second derivative is constant. It happens a lot that the second derivative will be constant. So you really need to get used to that. So it's sad because it's always negative. So then x equals 3 is a max. So we've just found the thing to maximize revenue for us. So question, what did x represent?
Is it the wait, hold up. Could you go up?
Is that enough up?
Yeah, number of changes.
Got it. It was my number of changes, my number of price reductions, my number of units, the number of times the units increase. So that 3 is not saying, oh, they should sell 3 pineapples. That's not what that x means, right? So we've got to be really careful in these type 3 questions because x will not be the units. So when we're going to question 5, we need to keep in mind that x is not the number of pineapples. So what is this question actually asking? I want to find the number of units and the price that must be set to maximize revenue. We just found the number of changes to maximize revenue. So then we're going to go back to our steps 1 and 2 and plug in to our purple and blue things. So my number of pineapples is 500 plus 20 times 3, which is 560. And my price is 31 minus 3, which is 28. Are we asked for maximum revenue? I can't remember. No, we're not. So in other words, to maximize revenue, 28 golden pineapples should be sold at 560 golden pineapples should be sold at $28 per pineapple. Oops. Yeah, a real bargain for our golden pineapples with miniature British people on them. It's like the borrowers. Do you guys know the borrowers? Does that mean no? You guys know the borrowers, right? Like the little people that live in your houses. No? The borrowers are awesome. Karigurashi no Ariete? No? No? You guys should check out the borrowers. They're awesome.
Is it from a movie?
It's a book and a movie and a TV show.
I don't know. I saw a movie with like little people. It was like some Japanese thing.
It could have been Karigurashi no Ariete. So Karigurashi no Ariete was they made a Japanese movie about the borrowers.
I don't know. I think I saw it. I'm not sure.
It's really good.
Do you know the name of the movie?
Karigurashi no Ariete. I don't know what it is in English though. I'm sorry.
Then I don't know.
Probably the borrowers, or maybe I don't know Ariete and her little people.
Do they live like under a porch?
Mm-hmm.
Okay, then I saw it. Yeah. And there's like a dollhouse and everything. Like there's something about doll. I don't know.
But you remember a house hippo that lives in your kitchen? What's that? What?
A what?
A house hippo that lives in your kitchen? What do you want to know how to write, Michael? What are house hippos? Should I know about that?
No, just because the word that you said, the Japanese or Chinese word you said sounds really, really complex. That's why I was like, yeah, how are you supposed to write that?
In English like this. Karigurashi, which means like to borrow things. And then it's no Ariete. And Ariete is just a name.
Oh, okay.
Right,
Yeah, I think that's the thing I'm talking about.
Gurashi no Ariete. Or like that. Okay, so yeah, that's totally it. That's Karikodashi no Arietti. You have seen it. Oh gosh, someone's seen it. That makes me really happy. It's really good. I'm sorry, I got really distracted from math because I love her. Okay, so our next option is we can do another fencing type question, another type 2 question, or we can go back and do a type 1 question, which we haven't done today. Which do you guys prefer? Because this is going to be our last optimization question together. The fencing, I've got 2 for fencing. I got 3 for type 2. All right, 3 people care. We're gonna go with type 2. So that means we're gonna do this number 8, and number 8 is not the easiest of type 2 questions, so I do think it's a really good one for us to do together. Let me know when you have read number 8. Tell me in the chat when you read it. Okay, that's a bunch of you. Let's do the problem. Hang on, am I gonna have space to do it right here? Do I? No. Okay, so this is type 2 question, and we know that with type 2 questions, it's usually really useful to draw a picture of what's going on. So here we have a Montreal aquarium that wants to construct a large rectangular prism fish display without a top. So we're like constructing a box here. So we're doing question 8. So we're just gonna start off by drawing this thing because it's type 2 and drawing it makes it easy to imagine. So we kind of have this fish display that's this like rectangular prism. That's my attempt at drawing a rectangular prism. Okay, so what function am I trying to optimize in this question now that I've drawn this thing? What am I trying to optimize? You got it. I want my minimum cost. So this says find the minimum cost to construct the display. So that's saying minimum, what minimum cost? I want to minimize my cost here. So when I'm thinking about that, it says the information that I'm given about cost is that the material for the base costs $8 per meter squared, and the material for the sides cost $4 per meter squared. So what I need to do here is find out how many meters squared are there in the base and the sides. Okay, so if we go back down and look at our picture, right now I'm not going to think about the rest of the problem at all. So I'm just going to say that this is the height, and we'll call this the width, and we'll call this the length right here. Okay, so how many meters squared are there in the base? in terms of that W and L that I have right there? What does a meter square represent? So not 2 times length times width. It's actually just L times W, right? A meter squared, the fact that we have this word squared here, that tells me that I'm looking for area. So the base is really just length times width, and I only have one base because we said there is no top on this thing. So it's not 2 times that length times width. There's only one base, there is no top. It does say that, but right now, like I'm not gonna think about that at all. That 2 is gonna come into play in just a second. Right now, I'm just saying W and L. That length is L, that width is width. But it will come into play in just a second, Alex. Okay, so then what about in the sides? And the sides, I have H times W. How many sides do I have with area H times W? Do I have 4? Be careful. I have 4 sides, but do they all have the same area? I got 2 of them. But then my other 2 sides, the height is the same, but it's H times L. So this is the 2 smaller sides. And this is the 2 bigger sides. So then we're told that my cost is $8 per square meter in the base. So that's 8 times L times W plus $4 for the side. So that's 4 times 2HW plus 2HL. So this is my cost for my base. And this is my cost for my sides. But notice what I did here. I really just kind of went through and looked at each of my sides separately. I'm like, first I have my base. My base is like that thing right there. Then I have these 2 pink sides. And then I have these 2 blue sides, right? So I'm just kind of looking at the area of each of my sides separately. Now, this is in terms of 3 variables. So I need to find a way to rewrite this in terms of just 1 variable. And this is actually a really challenging problem in terms of that, because there's actually 2 pieces of information that I haven't used yet. The first is that, as Alex pointed out, we are told that the base will be twice as long, the length of the base will be twice as long as the width. So this right here, this is my step 1. And when I move on to step 2, we're told that the length is twice as long as the width. What does that mean in terms of my W and my L? What relationship can I find between W and L? give you a hint. I can rewrite that L is equal to something. What is L equal to?
Two W.
2W, thank you, Luca. So L is equal to 2W. So now I'm just gonna go and replace that down here. So I can say that cost is equal to 8 times 2W times W plus 4 times 2HW plus 2H times 2W. So I'm gonna have 16W squared plus 8HW plus 4LW. I'm sorry, not 4LW, 4H. 4HW. 8, wow. 8HW, there we go. Oh my gosh, I can't do this. I can do math today. 16. This is a 16, guys. We got there. I got there. It only took me 3 numbers. Okay, what other piece of information did the problem give me that I have not used yet? Volume, you got it. So what is the volume? Oops. We also know here that my volume is equal to 72, but volume is also equal to length times width times height. But we also know that length is 2W. So in other words, we know that 2W squared H is equal to 72. So if I divide this on both sides by 2W squared, and it makes most sense to solve for H in this equation because I have W squared and not just W. This gives me H is equal to 36 over W squared. So then my cost function is 16W squared plus 8 36 over W squared times W plus 16 36 over W squared times W. And these W's can actually cancel out, which gives me 16W squared plus 24 times 36, which you guys can do together, over W. Okay, I'm just gonna briefly talk through what we just did there since I especially had trouble with that 16 for a second. So we came up with a cost function by finding the area of each of the sides and figuring out how much it cost to make each of the sides. So we were able to come up with our cost function in that way. But then we said, I have 3 variables here and I need to only have 1. So what information from the problem do we have that we haven't used? And the first thing was that the length was twice as long as the width. So in other words, I know immediately that my L is 2W, and that's not really challenging. I can just replace the L with 2W. But the next thing that we know is that the volume is equal to 72. So that in that way, I was able to replace my H with something in terms of W. And now I have this cost function in terms of just 1 variable. Do you guys have any questions about how we got here? Because this is definitely a challenging type 2 question. And so these type 2 questions, you'll see what they're doing is they're really making you like imagine, what do these things look like? How many sides do I have? The same as the first one with the fence we did today. We had to be like, how many X's do I have? Here I had to think about the fact that, oh, I have 2 small sides and 2 big sides. Okay, now I have this in terms of just one variable. So I can immediately go on to step 3, 4, and 5, find my critical values. 16 plus 8 is 24. And so I just did that, but like you don't have to do it that way. You could do, like, this would just be, hang on, I'm gonna write this. This would be 8 times 36 over W plus 16 times 36 over W. So I just added the 8 and the 16 together to get that 24, but you'll see that these are like terms right here. And so you can just add them together in that way. All right, now we take the derivative of cost, C prime, and we get 32W minus 24 times 36 over W squared. Now I just want to remind you, we talked about this yesterday. That derivative came from the fact that the derivative of 1 over x is negative 1 over x squared. And that's a derivative that you should start getting used to seeing in this way, right? Like, it shows up a lot in these optimization questions, and it makes your life easier just to be comfortable with seeing that. So now I want to know where C prime is equal to 0. And this equation that we've ended up with is another type of equation that shows up a lot. So I have 32W is equal, or sorry, minus 24 times 36 over W squared is equal to 0. So 32W is equal to 24 times 36 over W squared. Which gives me that 32W cubed is equal to 24 times 36. And then I can just divide by 32. And I get that this is 27. And what is the cubed root of 27?
It's 3.
It's 3. So that means I get that W equals 3 here. And then I want C prime does not exist. When does that happen? When does it happen that C prime doesn't exist?
Never.
Not never. It's been never at every problem, but not this one. Is there any possible division by 0?
Oh, yeah.
You got it.
With 0.
You got it. So W is equal to 0, but that, what is W? What does W represent?
The width of the tank. So it doesn't make sense if it's 0.
Exactly, you got it. So 0 does not make sense. Clearly, I'm not going to have a fish tank with no width. The fish will not fit inside. So we get rid of 0. This doesn't make sense in the context of the problem. So then we move on to our step 4, where we find C double prime, and we do the second derivative test. And C double prime is 32 plus 24 times 36 times 2 over W cubed. And this actually maybe looks similar to something that we did yesterday. And here again, we're just kind of reminding ourselves 1 over x squared is equal to negative 2 over x cubed. And that's where that derivative came from. And then we're looking at C double prime, of 3. I don't care about that 0. It's not important for me. So is C double prime of 3 positive or negative? You got it. It's positive, so we have greater than 0 here. So it's happy. So is x equals 3 a max or a min?
Minimum.
It's a min, which is what we were hoping for. We wanted to minimize cost. So this brings us to our final step, which is now that we've found our critical value that works, we answer the question. And the question was, find the minimum cost to construct the display. So I actually want my minimum cost here. And what should the dimensions be? So I want to find cost and dimensions. And what I have is that W equals to 3. So what is my length? W is 3. If my width is 3, what's my length here? You got it. It was 2 times 3, so that's 6. And then my height, remember our formula for height here. For these type 2 questions, we want to go back to step 2. And here we found that height was equal to 36 over W squared. So I'm plugging my W into that. So my height, actually, I wanted to highlight that too. My height is 36 over W squared. So I'm going back and I'm plugging in to that. So this is 36, over 9. Which is 4. And then the cost itself, we're going to plug that W into our cost function. And we get this is 16 times 3 squared. What was our cost function? 24 times 36 over W. Plus 24 times 36 over 3. So the dimensions should be 3 by 6 by 4 for a minimum cost of $432. And that is my final answer. Are there any questions about what we did here? This type 2 question is definitely on the more challenging end of type 2 questions that you could be asked. I'd say it's probably, you're not going to see one more challenging than this one. Are there any questions about this? About these type 2 questions, about this question?
Would something like this be on the final exam?
It could be.
Could be, okay.
When there are fencing questions, they typically are more like the one that we did at the beginning of today with the seaweed, where you like separate like that. But in the past, you have occasionally seen problems like this. Another type of question that shows up pretty regularly in terms of these type 2 questions is when you have a frame and you want to like maximize the area of the inside. And so if you go to the practice set, there are a few questions like this one.
Yeah, that was on the Cal exam last year. A
Yeah.
question like that with
Yeah, so like these show up pretty regularly, but they're also really similar to the like seaweed one we did. All right, guys. Clearly, I'm not going to do another question today. So we're done with optimization. I recommend trying to do question 4 on your own, because that's the only one we didn't do from this. And the decimals are the thing that make this question hard. Like there are all of these like giant decimals in here that you have to be careful with. So I recommend doing this question. If you can, if you have time, please do it. Other than that, we're done. Next class, we're going to learn elasticity, which is our last topic. Oh, there's lots going on over here in these videos.
Yeah, I'm babysitting my little brother.
Oh, hi, little brother.
So,
All right, guys.